In this video, we're going to be working monads through the definitions and laws. Let's talk about algebra. Let's look at 1 plus 1, numbers and addition. We can give a simplified definition of an algebra as something that has these things: a set of objects and an operation on this object that returns some new object from the set. We should also consider the rules or the laws that these operations must obey. Note that x equals equals or x equals y means that you can replace x with y and vice versa, and the result of the expression won't change. An algebra gives us the ability to talk abstractly about the objects and the operations while considering the laws that these operations obey on the underlying set. These concepts could be transferred to functional programming. We just need to twist the definition a bit to include the types and functions. Algebras or algebraic structures could be used to create nice and simple APIs that are supported by laws. Let's look at somewhat simple algebra first, called monoid. We will start by looking at monoid examples first. For example, numbers with a plus operator. You can add two numbers together, and it doesn't matter in which order you add these numbers. Also, adding a zero doesn't change anything. Another example is list with concatenate operator. You can add two lists together, and it doesn't matter in which order you add these lists, and adding an empty list doesn't change anything again. And we could generalize this using monoids. A monoid is a set of elements, for example numbers or lists, a binary operator on that set, plus or concatenate, and an identity element, for example 0 or empty list. An identity element is a neutral to this binary operation, which means it just does nothing. And the binary operation must be associative. We use type classes to implement algebraic structures in Haskell. A is a type of elements. Mempty is identity element of the monoid. And this operator called append is the binary operation of the monoid. A monoid also comes with laws that needs to be proven outside of the definition. Right and left identity laws state that adding nothing to an element or adding an element to nothing doesn't change the element. And associativity law is following. In this case, x equals to y means that you can replace x with y and vice versa, and the result of the expression won't change again. So if you or the compiler need to refactor or optimize something, these expressions are guaranteed to be the same or interchangeable. We can revisit lists using monoid operation. We replaced or abstracted the concatenation operation with append and an empty list with mempty or identity element, and the behavior remains the same. Now let's fast forward to monad. Here's a definition of a type class and the laws. Let's zoom in on each of these pieces separately. Monad type class is represented as a type constructor M with two functions, the bind operator and pure, also known as return. Note that we are going to use pure and ignore return, but you'll definitely bump into return in the real life. If you're curious why this happens, look in the course notes. M is just a type constructor, for example maybe, list or IO, and roughly speaking it abstracts over some computation or effect. This M or a given data structure or a given library determines the behavior or effects of M. Let's take a closer look at these functions. So it takes a value of type MA, it takes a function that based on this value returns a value of type MB and returns a value of type MB. This one, given NA, makes a value of type MA. In other words, pure takes a value and lifts it up into a monad. All instances of monads type class should satisfy the following laws: left identity, right identity, and associativity. Let's look at them one by one. First one says that the pure A binded into F is the same as FA. The left identity loss says that if we lift a value and bind it to a function f, it's the same as just applying a function to a value a. Here's how the left identity law looks in the do notation. You don't need to lift a value into a monad just to bind it right away. You could just use the value. Note that if you're wondering how the do notation works, you can read about it in the course notes. And the right identity law says that if we take an m, a value with some effect, and bind it into a pure, it's the same as doing nothing to the original m. Here's how the right identity law looks in the do notation. It's quite similar to the left identity law. Both identity laws specify the behavior of pure. They assert that pure A does not do any effect, they just result in A. Thanks to it, you could trust that pure on list won't sneak any random values into your list, and pure on I/O won't perform any side effects. It just returns the value of its result. The law of associativity says that bind operator doesn't care how the computations are nested or grouped. It only cares about their order. Associativity law constrains what bind is supposed to do. We can refactor the law a bit to make it cleaner and clearer. When you have a chain of computation, it should not matter how they're nested. You could refactor, inline, or extract them as you wish. And here how the associativity law looks in the do notation. I'll repeat what I just said. It should not matter how the computations are nested. We can refactor, inline, or extract them as we wish. And that's it. This is a monad. But on the serious note, in reality, Haskell definition of the monad type class is a bit different. The pure is actually called return. There are extra functions. Applicative is a superclass of the monad, and their relationship comes with even more laws. It can also look different depending on the GHC version. But honestly, it doesn't matter. Whatever the definition you're trying to learn, it's not going to help you to understand monads. Knowing the definition of a chocolate cake is not going to make you a better baker. And there is also very low chance that you have to define your own monad instance and prove its laws. Just to re-emphasize, don't read monad tutorials. But if you want to keep working on the puzzle, feel free to check out the rest of the course, including the exercises to test what you learned. Thank you for watching.